simple harmonic motion. Let us discuss about SHM. Observe this simple pendulum. The resting position of the bob is known as mean position. One complete to and fro movement of pendulum about its mean position is known as an oscillation or vibration. Observe these points in simple pendulum. Simple pendulum oscillates about its mean position. Acceleration and displacements are in opposite directions. Acceleration should always be directed towards its midpoint. In other words, the above are the conditions for a body to be in SHM. Definition of SHM. A body is said to be in simple harmonic motion if it moves to and fro about its mean position such that at any point its acceleration is directly proportional to its displacement in magnitude, but opposite in direction and is directed always towards the mean position. Mechanical wave, sound wave. In this example, a mechanical wave, like sound wave, propagates as a result of simple harmonic oscillations of the particles of the medium. Projection of a particle performing uniform circular motion on a circumference of the circle makes same displacement in same intervals of time, t.
Nano World. What is nano? Nano is a unit for measuring the extremely small. Nano size is measured in nanometers, which is 1/1000th of a meter. How much is a billion? For example, let's look at an emperor penguin. Let's zoom in on the emperor penguin's skin. This tick is about 1/1000th of a meter. The bacterium attached to the tick is about 1/1,000,000th of a meter. And there is the bacterium's DNA. The DNA's radius is about 1/1,000,000th of a meter. That is 1 nanometer. DNA is made up of many atoms, and atoms make up all matter. This is the nano world. This nearly invisible world can be viewed with an atomic force microscope.
When an electric current is passed through a conductor, some of the energy is lost in the form of heat and light. The amount of energy lost varies depending on the individual material's electrical resistance. Some materials, like copper and gold, are great conductors of electricity and have very low resistance. Scientists discovered that the colder these materials are, the more conductive they become. But no matter how cold you make copper or gold, it will always show some electrical resistance. Mercury, however, is different. In 1911, when scientists cooled a sample of mercury all the way down to 4.2 degrees above absolute zero, its resistance abruptly disappeared. The first superconductor had been discovered. Gradually, more and more superconductive materials have been found that show zero electrical resistance below a certain critical temperature. And when resistance is zero, electricity is conducted perfectly without any loss, and a current can theoretically flow in a closed loop forever. This has been demonstrated by scientists who have sustained electrical currents in superconductive rings for years without any measurable depreciation of energy. And it doesn't end there. Not only do superconductors have absolutely zero electrical resistance, they also don't like to let magnetic fields pass through them. Instead, the field remains at the superconductor's surface. This expulsion of magnetic fields is known as the Meissner effect. You've probably seen the Meissner effect in action in science experiments that look like this. A magnet is set on top of a superconductive material, and at room temperature, nothing really special happens, but when the material is cooled down to its critical temperature, the Meissner effect kicks in, causing the magnet to levitate, as if by magic. But superconductors can be used for much more than cool science tricks. These materials are used today in MRI machines, super fast floating trains, and even particle accelerators. But we can't forget that these superconductors have to be kept at temperatures near absolute zero in order to function properly. This is a main limiting factor in the practicality of superconductors. Fortunately, scientists have been busy finding and creating materials that become superconductive at higher and higher temperatures. For example, some ceramic materials undergo a superconducting transition at high enough temperatures that they can be cooled down using relatively warm liquid nitrogen. These materials are known as high-temperature superconductors, and they have revolutionized how and where we are able to use this technology. But still, always having to have liquid nitrogen at hand is extremely limiting. The goal for scientists is to create a material that is superconductive at room temperature. If we had room temperature